That's because of the but it's also, but in general, that's basically automatically like that's so I think it's mainly when for each algorithm component. I just if I interval then I'm curious. I saw the I promised like 2 years ago, but yeah. So did you try to look at the parameters? Like there's the approximation factor. I do, yeah. I don't remember what I used, but I remember it was there is no approximation. Yeah, there was some small. For me, it's mainly like choosing three ranges just to get a feel of, because depending on that's what I without
I'm going to reserve my seat.
Yeah. So you have a reading group, right? So I won't mind if you have to walk out.
So I'm going to stay until the end. I pushed it at 4:45.
Okay.
And but yeah, I think it's probably good if you stay in the
Yeah, I'll just stay here and then you text me and I'll show up there.
Okay. So we have to take until 6. So at 6 p.m. I don't know if your phone is going to work. Oh no, it's in the reception there. Yeah, the reception is almost outside. So I give you.
It works here. It works here.
Oh, is it here? Okay, yeah, no, that's okay. So then I will give you a call or a text when we finish. And one option is for me to come here so that
Don't worry about it. No,
okay.
I'll just walk there.
So you know the street when it's called Forbes. So if you go left on Forbes, it's almost the next street. It's called Craig. I will give you the address. It's
that's right.
It's the next place. Yeah, these days with Google.
Google iPhone app like that.
Okay then.
Cool, yeah, it's fine. Just text me the address and I'll show up there.
How is the apartment?
Oh, it's good. I mean,
Is it a 2-bedroom or one?
They give like a 1-bedroom suite. I mean, but it has like, it's like an apartment. And I'm like, wow.
What I like is the apartment.
But they made me sign that no parties.
And sign. You can maybe party outside that. You can.
I don't know. I mean, the first time I'm signing that.
Yeah, that's funny.
I guess a lot of people did that, right? They're like, oh, looks like a
Because an apartment also. I love it. Are you in that? Because when you check in, are you in that building or
another building.
Okay, I wanted you on that building.
Yeah.
Because it's really cool. You must.
It's like, yeah, a couple of blocks from there.
Okay, but then you're tired. The Walnut Street is the nicest neighborhood. So.
Is that where you live?
Yeah, I live around there.
So often this is up?
It is. I'm 20 minutes. The morning I need to leave at 8:38. If I leave at 8:38, then I'm there at 9.
Timed it, right?
Yeah, don't have to wake up too early. I think people don't drive too much. And you're not.
or bike?
Half of the people bike or take the bus,
Yeah, yeah.
and the other half drive. That's really, of course. Okay, so we'll, before we aim, I love the term aerial. I'm not going to be able to say aerial informatic. Okay, we'll start. We'll close the door because if we let more people in, that's really exciting. Thank you all for coming here. My name is Louis-Philippe LP. It's a pleasure to introduce Ashish. Little thing, we both did our PhD at MIT, so I know him for a long time. Already did amazing work early on affective computing, human in the loop interaction, and then went and almost created or at least pushed the field of aerial informatics, and that's what he's going to present today. So it's a great pleasure to have him. Thank you very much.
Yeah, thank you, LP. Oh, can you guys hear me well? Okay. Right, thanks for coming to the talk. And
Maybe a little bit louder, or do we get...
okay. Yeah, I'll try to be as loud as I can.
Okay,
Okay,
so
that's
louder,
not for the.
yeah.
Okay, okay. So today I'm going to talk about some of the work that we've recently done in our group, and a lot of this work is actually being motivated from the Yale robotics perspective, and there are a lot of collaborators. I mean, you might recognize Day. I mean, he was a student at Robotics Institute, and he's a partner in crime, and a bunch of students and researchers at Microsoft Research. And the thing is, of course, I'm talking about safe and optimal path planning in skies, but there are a lot of interesting techniques that Yale Robotics is just an application to. For instance, I could have given this talk under safe and optimal planning, under uncertainty, for instance, right? So a lot of the things that I'm going to talk about are much general. But the mission of some of the things that we're trying to do is really try to enable safe autonomy at a scale, right? This day and age of self-driving cars, and right, we are actually starting to think about safety and autonomy at a very fundamental level, right? And when you think about safety and autonomy, the stack, right, is pretty complex. It's not just one theoretical model that you're developing, right? You have to start thinking ground up from systems where your OS is secure, right? Sensing, all the robots in the world, right, probably have machine learning and perception system, right? It's not far-fetched to say that they won't, any of these guys will have some kind of pattern recognition going on, right? And given those machine learning systems, you need to start thinking about control and high-level planning, right? So how do you enable that? How do you enable that skill? That's the high-level mission of some of the work that we've been doing there, right? And I'm particularly going to talk, about the aerial robotics domain, and mostly because that's the focus, and that's something that I'm passionately following these days, right? So when we talk about, think about flying objects autonomously, right? Yeah, they're in the uncertain world, so there's uncertainty, right? There is constraints imposed due to the system dynamics, right? And then there are constraints due to what you can enable in terms of computation on board on a small device, right? So there are all of those kinds of challenges that we need to start thinking about. When you start thinking about safety, you are in an uncertain environment. There are a lot of latent variables. So how do you reason about them? And especially if you have a machine learning system on board, right? You know that none of these machine learning systems are going to give you 100% accuracy. So there are errors in it. So if you have errors in it, how do you then reason about controllers and planners? Right. So let's get directly to it, right? So here is the one. We'll start with estimation problem, right? The first problem is if there's uncertainty in the world. Let's try to estimate it as well as we can. So this was I would say the seed project that really spawned all our efforts in this space. So this was done a couple of years ago. And this was the realization that anything that's flying in the air, the wind is very critical to it, right? So imagine if you have a quadrotor, right? What's the maximum speed a quadrotor can fly? Like some of these high-performance quadrotors can go 50 miles an hour mostly. But some of them, probably not so, like 10 miles, 15 miles, 20 miles an hour. If I have a headwind of 10 miles an hour, my effective range that I can go is halved. Right? That's a big thing, right? You have to plan appropriately. And of course, you have weather reports, sure, you might have some kind of predictions, but this might, I mean, these predictions are pretty stale. So we started looking into this problem. So if you think about the current the current state of the art in wind sensing, what you have information from satellites, right? You have satellites going in space, and they are giving you some kind of imagery. All that imagery goes to the weather models, and then you can do some kind of simulation. But this information is both sparse in space and time. You basically have narrow bands that you're covering as you're going through it. Then you have ground stations. You have all these weather stations, right, at the airports, and they can observe, and they can, again, but they are limited. Spatial, the resolution is spatially limited, right? And then here is an active, almost active, I would say, sensor. So these are the weather balloons, and they are deployed, around. These are 160 measurement locations, but around 200 or so locations. They are released 6 a.m. and 6 p.m. by NOAA, and these guys have all these instruments on it: GPS, wind, pressure, temperature. Right? They climb through the atmosphere. Will go up to 90,000 feet, rupture. There's a GPS on it, it'll beacon, and someone will go and collect it. Massive operation, right? This is one of these balloons is probably cost point of $1,000, just the equipment itself. Some of them are lost, right? So it's a multi-million-dollar operation going daily just for these purposes, and this data gets fed in, right? And so again, the whole point of the slide is to say that wind prediction is there, but it's pretty limited, right? I mean, if you're working with flying vehicles, or if you're a pilot, you would know that you are taught never to trust wind prediction. Always plan for the pessimistic case, right? And it's some of so the first question we ask is, how can we sort of leverage, existing infrastructure to make improvement in state of the art in wind prediction, right? So again, just for clarity, here is the wind measurement systems. So this is a map of winds aloft stations. So what you have is you have our weather agency, NOAA, and they would report weather, specifically winds at different altitudes at all these discrete locations. So if you look at state of Washington, there are 4 or 5, right? You have few in the Northeast. So it's pretty sparse in space and time. However, I'm going to give you an image of all the airplanes flying in the air right now. So if you just go and query, right, on the web, like give me a map. So this is Flight Radar 24 if you go on this website. There are around 10,000 airplanes in the air at this moment over continental United States, right? So you can think of this as, each of this airplane is a potential sensor, right? So is there a way to harness information from this to build wind predictive models? Again, the problem with these things is that there is no central data set where all of these guys are beaming the wind information, for instance, right? It can be a giant exercise in corporate management and trying to convince all the airliners to share the data as well, right? So there are interesting challenges. But so here's a cute technique that we developed, right? And it's heavily relying on machine learning, right? And to the point that we only want to harness publicly available information, not even try to contact FAA or any of these corporate airliners. Can you even do that, right? I'll give you intuition. The intuition behind this technique is very straightforward. If you right now query, say for a flight, say flight status, Seattle to Boston, Alaska Air, this, right? Google or any search engine will tell you, all right, so much, 3 hours, 41 minutes to go, and the airplane is over this place, right? So what you can do is you can actually look into this information, and this will have signal about whether your flight is getting headwind or tailwind. And the rest is details that I'm going to explain, right? So how can you use aircraft trajectory as wind sensing measurements? So for instance, in this case, imagine the red line is the direction to which your vehicle is pointing towards, right? And you have some wind that's acting on it. And because of that, the resulting trajectory is the green one, right? So it's a a vector triangle. This is, you can observe. This is observed track and ground speed from GPS, for instance. right? If you have the heading in which where the nose of the airplane is pointing and the airspeed that's going which, then you can just simply do vector math and you'll have some signal, right? The question is, can I get any information about any of the other vectors, right? How can I get vectors to resolve what my blue line is? And the way you do it is through web queries, right? So there's a flight radar 20 for the same software. If I just hover over it, it'll give you, on an airplane, it'll give you, all right, this is the latitude, longitude, and this is the altitude. So I know the position, right? Right. So that's good. It also tells me what? It tells me that it's 0 feet per minute, so it's in a cruise mode. It's tracking 125 degrees at 500 knots, right? So what we got is basically, we got this green vector, right? From that information, it's just a single web query. I'm not doing anything special with that. I don't have any information about this and that thing, and I have no information about this vector at all, right? So it's an ill-defined problem. Sure, I have some information, but it's partial, right? I still have to work at it. And one way to work at it is, you go a little bit deeper, right? You look at their flight plans, for instance. So in this case, there is right? Again, you can do this via web queries. You can basically see this following, right? This airplane planned for 450 knots, which is basically saying that if I had static air, this is the speed that I'll go at. This is the airspeed. But I'm actually going at 505 knots, right? It's kind of giving you some kind of, idea about the magnitude of this vector, right? It's saying that, all right, you might not know the direction, but I know the magnitude. So there is still, the direction is latent. That's hidden from you, right? So if you guys have taken machine learning course, one thing that you can do to resolve, right, the uncertainty is use some kind of an EM-like technique, expectation maximization, where you will resolve spatial smoothness. So what do I mean by spatial smoothness? So for every airplane in the air, you have this wind triangle associated with it, correct? So one simple assumption I can make is that, any two airplanes that are close in space, the blue vector is the same, which is a very reasonable assumption to make. It's a spatial smoothness assumption, right? And that's what gives me the way to bootstrap all this data off, right? So what we do is basically we use spatial smoothness assumption. And here is a resulting graphical model that basically we'll use to reason about. And I'll go through all these details, right? But again, just to recap, what we have got latent information. The latent information in our case is the heading of the airplane, which we don't know. And what we're going to do is we're going to resolve it in a graphical models framework. So W, the big W in this image, is your wind field. This is the wind field over the entire continental United States, for instance, right? And then you have these wind station observations coming from NOAA, and say, all right, whatever NOAA is saying is nothing. It should be close to W, but it's a noisier version of it. So let's not throw that information. Let's at least subsume that. Right? So you subsume that, right? Forget this is. I'll come back to it. But this is a potential function, right? That is basically saying that first, all the airplanes that are close to each other should expect similar winds, and those winds are constrained using the wind triangle, and that's what this potential is intuitively trying to combine, right? So once you have that, you can run a Bayesian inference procedure to get a posterior distribution on the wind field, right? So whenever you have a test site T star, you basically say, all right, this is the posterior distribution over W, right? And you can infer from that, right? Again, there are a lot of details on how to do the Bayesian inference on this, but the intuition is you exploit spatial smoothness with the physical property of the wind triangle in order to reason out. The resulting algorithm is very akin to an EM kind of algorithms where you hallucinate directions, reason about, and see how it fits the data well, and then you keep doing those kinds of iterations, right? So it's a pretty simple trick. The question is, how do we validate this thing works? No one knows ground truth up in the air, right? So we did some field studies. So this is one particular day a couple of years ago where NOAA was predicting that this is what the wind is going to do. So this is the states of California, Oregon, and Seattle, right? And we have another model. Let's not worry about this. But if we use all the aircraft information, this is our prediction, right? It's basically going much more towards north than what was predicted by NOAA, right? How do we verify that this is closer to the ground truth than that? What we do is we release a balloon, a weather balloon, and we try to predict its track, right? And we'll use this model and that model and see which one's closer, right? One data point, right? So that has a lot of caveats, but it's one way to do it, right? So when we did that, so this is, we released the weather balloon at in the Acadia National Park, and here are the different trajectories. The magenta trajectory is predicted according to the NOAA, so it's very much in line with the wind predictions, right? Blue is the what one predicted, and black is what it ended up being, right? So again, one way to validate that things are aligned. I mean, we have, this is a service online. So if any of you guys are working in this space, I know there's a lot of aerial work here. This is not really giving you low-level wind estimation, but at the high level, 3,000 feet and above, this is pretty accurate. So this is a service that's running live 24/7. Some airline partners, yeah, you have a question?
Spatial smoothness assumption, somewhat slightly broken? Is that why the actual weather balloon suddenly
No.
take apart?
So again, spatial smoothness can be in terms of XYZ, but you can actually also incorporate terrain features. So in this implementation, we just have XYZ, right? And those kinds of sharp turns you see. I mean, if you release a weather balloon, you'll see those kinds of patterns. And often it is, fast-moving streams. It's basically, atmospheric phenomenon where you have a layer of air that's sliding at a very fast rate. And it kind of shows that our model is not complete yet, right? Because you should be able to model that too, right? But yeah, I mean, as I said, right, what you can do is you can actually increase, the spatial smoothness does not need to be on the XYZ space as well. You can incorporate other variables, which can be the pressure, temperature, and things like those, right? All right, so this is a service. You can go and check it out soon. This kind of technique is very interesting in places where you don't have instrumentation. So this is, so India, right? They don't have this kind of density of weather balloons, but you still have airplanes flying over there, right? So we are extending all this thing to a global model to encompass these areas. So we did some experiments, and the experiments here is very difficult. The reason being the ground truth, right? If you want to do something at scale, like how do you get ground truth on this? So one way what we did is that we, given all the airplanes in the air, we try to predict the ground speed using different models, and then you can compare the error, right? And we have some measures. Recently, we've been also working with airline partners that are broadcasting their, the live data as they sense it. But I'm not at liberty to mention it right now. So, all right. But here's the deal. This is wind. Wind is 25% of your weather phenomenon, right? Other four variables being pressure, temperature, relative humidity. If I have a very accurate model of wind, I should be able to transfer that knowledge to other variables as well. So, why does wind occur, right? The physical phenomenon is mostly because of the pressure differential, right? So if I know very well the wind map, I have the potential of improving the pressure map as well. And if I know pressure map and the wind map well, it goes to temperature and relative humidity. And the cycle continues, right? So you have the structure in the space. And what you do is the following then. You take the same graphical model, but use constraints between wind, pressure, relative humidity, and temperature using some other graphical model. In this case, it's a deep network, but it can be anything, right? It can be if you know the physical process, you can encode it. In this context, we were lazy, so we used deep networks, right? And but again, I mean, deep network is also possible because there exists so much data in the weather phenomenon that you have like hundreds of years of for information. And if you think about it, that all the relationship between wind, dew point, pressure, temperature is arising because of the physical phenomenon, as opposed to as opposed to some very complex process. So you can actually model this very well with, I mean, we call it deep network, but it's really a two-layer network. So, but again, this is so we did some more results, encouraging experiments. Happy to chat more about it, but I want to go to other parts of the talks, right? So I motivated the whole problem with wind field, and then what you need to do is you need to plan around it. So consider this as a vortex, right? Air vortex. You have to go from source to a destination. The shortest path in time is a curve, right? And in order to reason about that curve, you really need to know what's the latent variable in there is, right? And of course, there's a lot of uncertainty around it. So how do you come up with the most efficient way to traverse from A to B under such kind of latency, right? That's the problem that you're trying to solve. So there's an interesting exploration trade-off. You do have some prior information coming, because of weather forecast models and things like those, right? So, but as you go through the wind field, you might find that what you are experiencing is very different than what was told to you. So then, should you explore? Should you exploit? Like, how do you resolve that tension, right? So this was actually Day's internship work when he interned with us, and what you can do is you can actually map it to a shortest path problem when the edge costs are not known in graphs. So consider a graph. You have a goal state and start state. And if you knew the edge cost, you can run shortest path, right? But in this case, you don't really know the edge cost. You have some distributions over it. And this distribution is arising due to the winds on it, correct? So if that's the case, what should an optimal policy be? And what can we say about this policy, right? How do you solve this problem? So, one thing to notice that the edge cost dependencies are very structured, especially in the wind case. The structure of the edge costs are due to the natural dynamics of the wind. And again, there is spatial smoothness is playing a big part in it, right? So essentially, what we got is a combination of something called a Canadian traveler problem. How many of you guys are familiar with Canadian traveler problem? So, okay. Yeah, it's an old classical problem, but where what you're really trying to do is that you are trying to navigate in a town where some streets might be closed due to snow, right? And there is a Bernoulli probability of if the street is open or closed, right? So how do you do that? So that's a very particular structure, but here the structure is arising due to spatial smoothness, right? So you can actually think of combination of Canadian traveler problem with Gaussian processes. And the kind of solution that we come up with is very standard. It's basically based on hindsight optimization. So here's what we're going to do, right? What I'm going to do is I'm going to sample, right? So I have a distribution, the wind fields. I can generate 1,000 samples very efficiently because it's sampling from a normal distribution. And corresponding to each sample, I instantiate a graph, the edge costs on the graph. And I can solve shortest path in those, right? So you solve thousands of shortest path algorithms. And then what you can do is you can basically aggregate, right? So for instance, in this case, you solve all the shortest path, and then you aggregate all of this information, right, to result in a Q function that could tell you what next edge to take. So you take the next edge, you get more information, you update your posterior distribution over the wind field, and then keep doing, right? So you can prove that this is an upper bound on the optimal and things like those, and there are interesting properties. The good thing about this is highly parallelizable, right? Again, you can do, test this algorithm against, simple baselines, such as if you do no replanning versus, if you just use the mean of your distribution and make a policy based on that. So things like those, right? And again, the details are in the paper on how well we do. But here is the kicker, right? When I'm looking at an aircraft or an aerial vehicle, discretizing leads to behaviors that are not very desirable. And one way to go about it is basically, you discretize your graph to a very high resolution in space, but that increases your computational complexity, right? So this year we had Wen Sun, who's a robotics institute. I don't know, Wen, are you around? Well, he's not here yet. So, but what he did was basically he said, instead of trying to think, using path planning on graphs, let's think of receding horizon control. So as an aircraft, at every instance, I have 5 or 6 trajectories I could take, or a family of trajectories I could take, right? And you can, based on your beliefs about the world, you take an action, right, in a receding horizon control manner, right? So the cool, again, I'll let Wen give you the details once this paper is out. But here's the cool thing. What you're doing is, you are borrowing a lot from the bandits literature, right? So in the following sense, you can pose the problem of choosing what's the best trajectory to take as a multi-arm bandit problem, right? And due to the spatial smoothness, there is a very interesting property that happens, right? Initially, when you have a lot of uncertainty, right, because all of these edges are spatially close to each other, you'll get similar kind of information. Sure, you might have made a mistake, but you'll get same kind of information, right? But you might do initially some mistakes, but because of the proximity, you get similar information, and eventually you'll converge on something to do right, right? So in a sense, it's almost a sublinear regret algorithm, right? And which is a very interesting result, because now our computational complexity has gone down, and this is something that I can actually implement on an aerial vehicle, right? So actually, we ended up doing this. So this is a vehicle that that we have built, and it has 2-axis autopilot. So this is you see these autopilots that controls the elevator as well as the pitch. The great thing about this aircraft is that it's controlled by a avionics system based upon Ubuntu Linux. So you can interface it with ROS, and what we've done, pretty much implemented this algorithm on it, right? So here is a snapshot. So this is the EFS, right? Well, the resolution is not great enough, but this is my source. The destination is south of Seattle. And as the aircraft travels through, it's basically doing, it has EFS that gives you the wind information. It has a GPS, so it basically is building its model. And as it's going through, it's just planning. So instead of flight plan, you have a flight policy that you can follow, right? So we still have to do a lot of tests to validate that this thing is actually, working well. But, with that, I think I'll move to a topic that a lot of you guys might be interested in, which is safety of these kinds of methods and algorithms, especially for aerial vehicles. There is a lot of interest in thinking about plan and AI, safe AI kind of things. This is the world that we envision, right? You have quadrotors flying with, in autonomously in uncertain environments, right? Here is the reality, right? So I'll stop talking to take a break as well, and you can enjoy this. So this video was compiled by my intern last summer just to explore the envelope. And there's some pretty crazy examples. Most of them are actually operator error, if you notice, or wait for the grand one. Yeah. And this is the ultimate one. This is really trying to play with the nature, So basically, you get the picture. That's what the reality is, right? And uncertainty, all these accidents are happening a lot because of uncertainty, right? And the uncertainty in the environment is something that I'm going to talk about next. But when you talk about uncertainty, the uncertainty can happen in the system dynamics. Uncertainty can happen because your perception is failing, or because you don't have incorrect model of human, for instance, right? In this talk, let's just focus on the uncertainty arising due to perception. So as I said, robots, autonomous cars, all of them have perception modules that are working with humans, right? And we need to figure out a way to sort of live with the fact that machine learning system is never going to be perfect. And how do you do that, right? And to define the problem, let's just work on the quad order platform. So you have 3 degrees of control, your role and pitch. The state information is X, Y, Z, roles, their derivatives, the RPMs and things like those, right? It's a very challenging platform to actually think about safety. Why? Limited battery power. You don't have enough compute, let alone do all those reasoning, right? Something like this is a really crazy fly, as you might have seen. Tiny quad rotors, they are so sensitive that they get affected by the drafts in the room. So when in our lab we have to cover all the drafts to make them work, for instance, right? Every time this thing crashes on the wall, my system has changed. Because it's so light, my motor is now facing different directions, for instance, right? So the question is, can you, give safety guarantees under such kind of dynamic environments, right? And let's preliminary, right? State equation, right? And then what you want to do is you want to minimize a certain cost function, right? You have some kind of LQR control. You have some objective function. xt is where you are, x hat t where you want to be. You have some constraints on you. Control theory 101, right? Basically, you want to snap onto a red trajectory. You optimize this function. We know that the result of this this optimization is a closed form equation. It's a linear transformation of what current state you are, right? It doesn't have any constraints on safety, and that's what we're going to do. We are going to say we are going to optimize the same thing, however, with the constraint that we are safe. Right? Now the question is, how do you generate these safety constraints? How do you generate these safety constraints knowing that a lot of uncertainty will be coming from perception and machine learning? And even if you can generate these constraints, the second question that we're going to ask is that how can you efficiently solve this? Right? So that's a couple of things that we're going to talk about. And I'm going to borrow a lot of notations from formal methods community. So basically it's saying that x1 through xt, which are states, and u1 through ut, the controls, satisfy a certain property, and these are safety properties, right? So as I said, that the primary thing that we're going to think about is safety under perception and uncertainty, right? So another key ingredient of this is going to be the Bayesian inference or Bayesian classification paradigm. So again, to keep things simple for the purpose of exposition, let's imagine you have some data set and you're trying to estimate some kind of a regression function. So for instance, in a quad rotor case, I have a perception camera looking out. X's are images that I see. Y's are how far am I from the wall. Something simple like that, right? And you want to sort of do that mapping, and that's a machine learning procedure that's happening, right? What I'm going to do is I'm going to resort to Bayesian classification paradigm, which not only gives me, the prediction, but also gives me uncertainty around it. To just clarify things, imagine these are all the pink dots that were given to me as a training set. So someone took the quad rotor around the room, collected all these pink dots, right? And y's were the distances. So this is a supervised data set. I mean, we are going to use Bayesian inference technique that would give us the blue line, which is the fit, but also these variances around it. And what it's essentially trying to capture is the following. If I am in a novel situation, so if I am doing a real flight right now, if I see something, if what I see is near these guys, I'm going to say, all right, I have seen something like this in the past, so I know how to deal with it. Consequently, my variances are small. But as soon as I go something outside, right, I train it in this room, but my quad rotor goes out, right? The different lighting condition. You say this is something that I haven't seen, so I'm going to be very conservative. I'm going to give you big variances around my prediction, right? So that's the crux. That's the machinery that we're going to utilize in our control methodology, right? And I mean, a bunch of you might be familiar with it, but just for the clarity, I'm mentioning it, right? So let's see what happens. So if you have, your objective function, right? So what I'm going to do is I'm going to introduce probabilistic constraints here. So what I'm going to do is, again, for simplicity, imagine a linear classifier. You have a W transpose X should be less than B. What I'm saying is I should always be less than B distance from a wall, right? That's what this guy is. But W I mean, because of the framework that I have, not only I'm getting mean prediction, but also variance around it, right? So consequently, I need to have a probabilistic. Basically, I'm going to say that probability of this happening is very high. Chance constraint, basically, right? So we are employing chance constraints, and under linear Gaussian form, you can prove that, oops, what happened? This reduces to a semi-definite program, or actually a second-order Krohn program, right? So again, so the building block of this framework is going to be these predicates, which is basically saying that any state ST is epsilon safe, means that some function of that state, so mu is that some function of the state is greater than 0, if this is the most general form. In our case, let's assume a linear Gaussian form for these predicates, right? So there are some interesting properties of this framework. So the thing is, this allows to use a lot of machine learning systems. So basically it subsumes SVM, any kind of linear classifications, things like those, right? The appealing part of it is that in the end, the resulting program is often in the space of SOCP and semi-definite program. It's a convex program. So you can still hope to solve somewhat efficiently, right? More importantly, it allows us, so again, this is just a building block, but this is not enough. When you're looking at a robotic system, there are a huge number of sensors, a lot of things interacting with each other, right? So this is a building block. What you're going to do is we are basically going to add semantics and logic on top of it. So what I'm going to say is that you can have a condition that S is safe according to the predicate that I said, but I'll also allow its negation, right? I mean, you can also say, hey, why allow only these kinds of relationships? You can also be able to flip the sign. You can start to do ands and ors, right? Very important in sensor fusion. I have two different classifiers, one looking through camera, another ultrasonic sensor, third one barometric, all those things, right? So you can actually embed that. You can do ands and ors. You can say, you can, because you have ors, you can also have implication relationships. And I'll mention an example of that, right? Oops, this is behaving weirdly. Okay. And then you can have quantifiers. You can have globally. You can say between all this interval, I want these kinds of conditions to hold true. Or you can have condition 1 until condition 2 between this interval. So you can have all of these kinds of interesting behaviors that you can that you can encode very richly. So almost it's like a programming language that embeds machine learning systems in it, right? So here is the overall framework on how things work, right? So what you have objective functions, and you have these safety descriptions actually borrowing from the formal methods. I will say formal methods plus plus. The reason being, all of these safety constraints are parameterized with a random variable, right? So as the robot evolves, it's going to get more information. As it gets more information, your distribution over your random variable is going to change. Consequently, all of these are not static either. They are also evolving, right? So you have an interesting case where you have an objective function, but also the constraints that are changing as the quadrotor is flying in the air, right? And when we implement this on the real robot, right, we are actually doing it in a receding horizon manner just to keep things under control, right? So that's the overall framework, and I'll explain couple of examples. But do you have any questions or anything up to this point? Yeah.
Chance constraints are all linear.
So
linear system and then linear.
So the linear Gaussian form guarantees that you'll have an SOCP or SDP form, right? But if they are not, you'll have to figure out a way to solve it.
Okay.
Right, and but one thing to note is that it might seem limiting, but the linear Gaussian form subsumes, I would say, 99% of the classification that might happen. For instance, you can kernelize, and then you can write as a linear Gaussian form, for instance, right? But yeah, I mean, basically, if you don't have linearity, then you'll end up with an optimization problem that's, I don't know how to even solve it, right? Right. So here is a case study, right? So this is the quadrotor case that I'm talking about. We have a quadrotor looking out in the world, and you have a classifier that estimating how far you're from the wall, right? And it's a Bayesian model that gives you mean and uncertainty around it, right? And what you're going to do is you basically, from the training data, you're going to get a posterior distribution, and this is the condition that you want to satisfy always in order to stay safe, right? And the way you do it is you have a predicate, you basically boil it down. So this is the resulting constraint. If you open all those things, integrate over W, this is what you, it's a cone that you cone constraint that you come up with, right? So basically your optimal control problem is a constraint optimization problem, and you can compile it as a mixed integer SOCP. So mixed integer is really coming because of the OR constraints, and we'll get into the details a little bit depending on how much time I got. But here's one example. This is a very concrete example. What I want to do is I want to take a quadrotor that's at this state to the following state, right? So that's my optimization function that I want to minimize, right? Subject to the safety constraints. And here are my safety constraints. The safety constraints is that from all the points in future time, I want my classifier such that whatever state I come up with always satisfies this inequality with a very high probability, right? I mean, it's a toy example, but it gives you a sense of how you can write such programs, right? So you can have whatever objective function, in this case, an L2 norm, but yeah. Any questions on this? Right. Okay, so right. So what you're seeing over there, so the blue is the ceiling, right, and the quadrotor is basically trying to get to its goal, and as it nears the ceiling, what you see, the red surface, is basically the prediction on how far it is. So when it's very down low, it doesn't see anything. So it says, hey, my ceiling is infinity, but as it starts to go up, you'll start to see that it starts to see the ceiling, the posterior distribution over W changes, and it takes a maneuver that avoids colliding to the ceiling, right? So this is one simple example. You can go a little bit complex, right? The second complex model is, for instance, uncertainty in the battery model, right? So here's what we want to do. I want to make sure that I only fly high if I have enough battery. Why? Because if I don't have enough battery, crashing can be catastrophic. I don't want to take that risk. So how do you encode such constraints like that? So what I'm going to do is I'm going to define two different formulas, phi and psi, and what are these? So the phi is the formula. It's basically encodes the condition that in the next few seconds my quadrotor crosses a certain height threshold, right? And basically it's all saying that in the near future my quadrotor goes above a certain threshold. That's all. If it's true, then phi is 1, otherwise it's 0, right? So basically that's all it's saying. In future, between 0 to 3 steps, if any point z is achieves the threshold, I'm going to say that, all right, this happened. However, your psi can basically say that with a very high probability I have a battery threshold, then that's greater than some level, right? You meet that battery threshold criterion, and as we know, the battery usage is a stochastic variable. Why? So for instance, if I have a hovering quadrotor, if the wind is blowing really hard, I'll have to do extra work to keep there, right? So it's a function of stochastic environment around the world. So battery usage is not very predictable either, right? Here's a very simple model. I mean, it's not really realistic, but this is just to give you basically an idea. So then my safety invariance is that if phi is true, that implies that psi should always be true, right? So there should be no case where psi is true and psi is false, right? So you can encode that as an implication relationship. So it's just to give you a sense that what kind of relationships, what kind of structures that you can put in these constraints, right? The next question is like, I've shown all these toy examples for a reason. Trying to implement them in the real world is a mammoth task, right? I mean, that's some of the stuff that we've been dealing with like lately, right? So I'll give you an example. So this is a project that we did last summer. So this is what you see is Kirby Chambliss. He's a U.S. national air racer, and he participates in this in this air races. So this is a pretty complex circuit, right? So basically you have all these poles he has to go through. There are crowd lines, right? And he has to do these maneuvers, and he has to figure out what's the best way to do this. So, and when the wind is blowing, right, his turns gets affected quite a bit, right, because he's trying to make very tight turns. So how do you use the framework that I just described in order to solve a problem like this? And this is a very non-trivial problem even to encode as safety constraints due to the physical space of the nature, right? I mean, it's a problem that's not, I can't even encode it, right? So what we do is basically we have to move from safe controllers to safe mission plans and under uncertainty, right? So in the controller regime, we could write an objective function very clearly, right? In a mission plan, it might be tough, right? In the air race case, you're basically saying that, all right, minimize, but subject to all these constraints, and I can't even write mathematically those constraints. So it might not be easy to do that, right? So what I'm going to do, I'm just going to breeze through it very quickly because I know that, we have only, how long should I go till?
About 5-10 minutes.
Okay, so I'll try to wrap it up, right? So one thing to notice is that one of the reasons that these control policies are extremely hard is because they are mixed integer SDPs. Like if you have through lots of constraints, you'll come up with an optimization problem that's NP hard, mostly arising because you have mixed integers. And one way to solve it is relegate all of this to a planner, right? The reason you are seeing mixed integers is because you have constraints such as or and eventually. So intuitively what it means, if I have two windows that I can fly through, right? If I write the constraints, window left or window right, I'll have to look at all possible trajectories that are going through both of these things, right? So mixed integerness is really coming due to the or and eventually constraints. So what you can do is you can relegate to a planner. So consider this as a goal, right? You do a high-level flight plan through it, right? Instead of trying to solve a controller, you basically do something like RRT star or receding horizon, right? However, in order to reason about how to go from one vertex to another vertex in an RRT star kind of framework, you use the PrSTL, the convex PrSTL, because now you know that you only have the and constraints, right? So that's one way to do it, right? Basically relegate all your mixed integer aspect of your problem to a planner, and then at the lower level, you ensure that there's still safety between each of those branches, each of the trees that you're growing, right? I mean, we have papers on this, so I think we can, give you the details there. But here are a few examples. Again, a toy example where writing a PrSTL controller is going to be extremely hard. But if you relegate to a planner, you can do it reasonably, right? So in this case, we were just using, RRT star kind of things. But one problem that we still need to solve, still we are working on it, is I still have to solve an SOCP even, right, every time on a controller. So imagine if I have a fast moving quadrotor, I have to make some kind of control decision every 30 milliseconds. How can I guarantee that I can solve this guy in an efficient manner? Most of the SOCP solvers are iterative. So it's not even guaranteed that the optimization will finish before my deadline comes, right? So how do I even deal with that? So we have, some interesting works in collaboration with some folks in MSR India, Pratik Jain. I mean, they're optimization folks, and we're trying to see if we can come up with new algorithms that can solve these things very efficiently, right? And again, I think, what I'll do is I'll basically give you a snapshot of, some of the projects that are happening in future, and, I'd be curious to hear your thoughts on those. But, one of the things that we've been looking at is instead of reasoning about controllers directly as an optimization problem, relegating it to more of a simulation paradigm. So what do I mean by a simulation paradigm? So here is one framework that we're looking at. You have planners and controllers from robotics, from traditional literature, right, that propose trajectories, that propose plans. Then you have machine learning systems that are giving you inferences about the perception and things like those. And then you have these formal methods that are giving you constraints, right? So what we're going to do is we're going to let them operate independently first, right? The whole, the problem is arising because they're all talking to each other, and it's a massive optimization problem that's a mess to solve. But let them first do their own thing, right? And there's an efficient process to do that. Then what we're going to do is we're going to look at the probabilistic programming paradigm, where we basically simulate the world, right? We say that, all right, this is what your, these are what your classifier says, that here what the uncertainties look like. So what I'm going to do is I'm going to take each of the trajectory that you proposed, and I'm going to simulate in all of these uncertain worlds and see if they make sense or not. And I'm only going to accept it if, with a very high probability, they are safe. And these safety definitions are again, so it's a checking as opposed to using this as a constraints, right? And this day and age of multi-core processing, I think we can do that much more efficiently, right? So that's one direction that we are, where we are pushing. The other thing that, this is, this again, Wen's internship work, where we are looking at, the idea of safety in Markov decision processes and bandits and reinforcement learning, right? So what I talked to you about was doing control, right, with safety constraints, but there is no reason why you shouldn't be able to do reinforcement learning with it. Right now, the state-of-the-art reinforcement learning in safety is that you'll encode most of your safety information as a single dimension reward function, right? If this state is unsafe, reward is high negative, right? That's pretty much you can do. But you can actually do it via PrSTL kind of framework. And the reason this is exciting, because now you have some structure, some insight into the structure of the risks, right? And you can embed that in your policy in a very intelligent manner than what could be done before, right? So that's some of the things that we're looking into future. So this is the work that Wen did this summer, especially just on the bandit setting. We didn't make the whole jump to the reinforcement learning, but in the bandit setting, we have some interesting results that show sublinear regret policies under certain weak assumption on the risk structure. And then this is work with Sanjeevan, so he's here, and we've been looking at safe exploration, right? So instead of your objective function being minimum distance or PID or LQG kind of controllers, if you have saying go and explore the world, right? So how do you first learn the policy, and then eventually we'll also look into how to incorporate safety in it, for instance, right? So yeah, with that I'll conclude. So here's my email. This is a very young program. I mean, we started a year and a half ago, and I hope with this talk you got a sense of the spectrum that we cover. It's at the intersection of ML. We have a lot of computer vision based projects as well, which I didn't get a chance to get into, but you're welcome to sort of send me an email. We are always interested in working with students. We have a rich internship program, so please do give us feedback and talk to us. Right. Thank you.
We have time for a few questions. Yes.
Yeah.
So one of the bottlenecks was that you got an SOCP, and now the challenge is how to solve it quickly.
Yeah.
So I'm assuming that you got the SOCP from the probabilistic constraint at the position, and assuming that the noise is Gaussian, you convert it to SOCP. Why wouldn't one instead want to use a simple MPC and impose box constraints on the position? As soon as the quadrature is getting close to a wall, we just keep updating the width of the box in which the position is constrained to be.
I mean, here's the deal, right? You don't really know what the box is, and that's the reason you need to go to SOCP. If you know exactly what the box is, then there are linear constraints, I agree. Then you're solving a mixed integer linear program. But if you don't know where the wall is, so that's the problem that we're trying to solve. You don't know where the wall is, and as you come near the wall, you start to get signal about it, and quickly you reduce the uncertainty down, right? So that's the reason you have to go to SOCP, because you exactly don't know what the box is, and you'd rather be safe, but also you don't want to be too conservative either, right? So.
Any more questions?
Stun the room into silence. Yeah.
Just one thing. Could you you mentioned some paper conferences where you published some of the earlier work on the wind prediction.
Yeah.
Could you mention what papers they are?
Yeah. So I think IPSN. So that's the Airplanes Aloft. So that's where we publish that work. And then we have a follow-up work in KDD that came out. Yeah.
What does IPSN?
So that's information processing and sensor networks. Yeah, thanks for reminding me. Yeah.
Yes. And so in this, in the earlier version, you talked about wind. Do you also talk about other moving objects, or that's also in the same network right now?
Yeah, I mean, we are looking at the multi-agent optimization as well, and that's a harder optimization to deal with. And yeah, I mean, it's in works, but very preliminary right now. But yeah.
Are you already thinking?
Thinking a little bit about it. Yeah.
That's really interesting.
Yeah.
How much information do they need to share also to make it safe? Is it part of the equation?
Yeah, I think there is an interesting question about the theoretical limits of in terms of like your machine learning perception system, and the limits on your control given the uncertainty in the world, right? So for instance, your quadrotor can do crazy kind of things, but not all of them are safe. So in the worst case, what are the trajectories you should be pruning because you have certain kind of a noise model and things like those. But yeah, I mean, these are, as I said, like we're just getting started on it, so hopefully, it'll be good to hear your thoughts if you have some.
One more questions? Okay, let's thank the speaker.
Right.
And I think